So a metric partial map in MMP usually consists of a partial map of following types. So one type is the divisorial contraction. Means that we contract, so we have a contraction from y to x, and we contract the divisor into a variety of smaller dimension. So sometimes we might denote it as type, say C or D prime, where D denote the dimension of E, and D prime denote the dimension of the image. And so these are one of the typical elementary partition map in model program. And another type of elementary partition map, of course, consists of flops or flips. Okay, so the goal today is try to say a little more about what can we say in dimension 3, especially. So how much do we know of this elementary partition map in MMP, especially in dimension in the case of dimension 3? Okay, so in the case of dimension 3, then basically we are considering the divisorial contraction of type 2, 0 or type 2, 1. So this means divisorial contractions to a point. And in this case, we are considering the divisorial contraction to a curve. Okay, so these two types of contractions is going to be the main topics today. Okay, so maybe let me recall a little bit about what we know of the contraction to point. So divisorial contraction to point. So that I can say that we know this kind of contraction pretty well. So first type of result is basically due to Mori when y is most contract to the threefold, small threefold, then we know this is nothing but a blow up of a smooth point. So this is a result of Mori, and actually what he did is something more. He showed that if we start from the smooth threefold, then the image there are several more possibilities. So for example, could be a smooth point, or could be a single threefold, but contain the very mild singularities. So this kind of singularity is defined by, for example, like x squared plus y squared plus z squared plus u squared, or x squared plus y squared plus z squared plus d squared plus u to the cube. Or maybe we might have a single threefold and p in it, and this point is a cyclic quotient point of index 2. Okay, so this is a kind of well-known result of Mori. And following the similar directions, then one can also try to consider where y has mild singularities. For example, if y has only Greenstein singularities, then we can try to classify possible divisorial contraction to point. And so this work is done by Bielkowski. Okay, so then there are more possibilities, but basically the structures are very similar. But as you can imagine that we cannot keep doing this forever, because whenever we start from some singular threefold, then we end up with something might even more singular. So another another way to consider to study the divisorial contraction to point is try to consider what type of contraction to point if we impose a condition on the varieties downstairs. So suppose we know the variety downstairs is a smooth threefold, then by the result of Kalkita, we know that phi is a multiple of weight 1 m n, and moreover here m and n are certain positive integers related to prime. Okay, so in this case, if we consider contraction to a point, to a smooth point, then we know that the upstairs the threefold, the terminal threefold might have some cyclic quotient singularities of index m or index n. And so following this direction, then Kawakita, Hayakawa, and students of Hayakawa. So let me say it: Kawakita, Hayakawa, and Yamamoto. So this is a combination of the series of work. So by combining the result, we know that if phi from y to x is a divisorial contraction to the point in dimension 3, then phi can be realized as a weighted blow-up. So let me be a little bit more precise about weighted blow-up. So we say that it can be realized as weighted blow-up means that x is embedded into certain affine space, and actually in this case it's embedded in 4-dimensional affine space or 5-dimensional affine space. And more precisely, there's an embedding and wait.
Maybe to a quotient, Jungkai.
Yes.
Maybe to a quotient of A4, A5.
Oh, yes. Thank you. Okay, so to a quotient of certain cyclic group. Okay, and then and the weight either to A5 or A4 or A5, and such that Y is the proper transform of the weighted blow-up. So this is a weighted blow-up with the given weight above. Okay, So the result says that in the case of threefold contraction, divisorial contraction to points, then everything can be described very explicitly. So either we have a 4-dimensional embedding, or sometimes we might need a 5-dimensional embedding, and then we have a certain appropriate weight, such that we can just realize them as a weightable of in this embedding. Okay, so and the main ingredient behind this theorem basically consists of the following. So the key ingredient the first part, of course, is the classification of 3-dimensional terminal singularities. Okay, so we know that it's a known result mainly due to Mori and Mas-Reed that the 3-dimensional terminal singularity can be classified as a compound to vowel singularities, and maybe quotient by certain secret group. So, and okay. And the second key ingredient in the work is that basically they consider the push forward of the shape of this form, where E is the exceptional divisor, and Y is the threefold aspect. So mainly they consider the shape of this form, and if we consider the direct push forward, then it's going to form especially this is played a very important role. So considering this, and plus the so-called singular Riemann formula, then what we can see is that the ky plus r equal to the phi star. If we considering the ramification formula of this form, then A less or equal than 4, except some very exceptional case, except some cases. Okay, so basically these two are the main ingredient of the argument. So since we know the discrepancy here is bounded, so then it's possible to classify the divisorial contraction with bounded discrepancies. And for those exceptional cases, then it's also possible to classify by some further technique. So it's been a series of work of Kawakita and Hayakawa to really work out the project to classify all divisorial contraction to 3-dimensional divisorial contraction to points. Okay. So my goal today is try to explain our approach to study the contraction to curves. So let's consider the divisorial contraction to curves. Okay. So maybe let me recall a little bit about some previous work. So so we are considering the contraction of type C21. So some previous known result is okay. Okay. So first of all is by Mori, that when y is smooth, then we know the contraction is going to be blow up of x along the smooth curve. So C is a smooth curve inside the smooth threefold. Okay. And also Kakowski has some extension of this result. So Kakowski classified the case where y is constant, and he can show that x is smooth, and the curve here, and y is realized as a flow up along the curve inside the smooth threefold. But now this curve is a locally contained section planar curve. Okay, and perhaps the most systematic work is done by Zerdas. So Zerdas he tried to consider the situation that we have a divisorial contraction to a curve, and the curve itself is smooth, but the x could be the threefold could be singular. So he has a series of working on this kind of situations. So our expectation is we hope that for any divisorial contraction to curve, that then there is a embedding x into certain affine space such that y is the proper transform of a vertical. Okay, so we our goal is try to show that we have some work in progress along this expectation, and we expect that this is possibly true, and also we expect that there's a embedding into dimension up to 6, such that the vertical is really not really too complicated. Okay. Okay, so let me explain to you what's our approach. So we are given a divisional contraction from y to x, and contracting the divisor to a curve C here. And since a terminal threefold is embedding, can be realized as a compound without singularity quotient of compound without singularities. So we might have a affine space, 4-dimensional affine space to start with. So then what we try to do is that we can try to embed into the high-dimensional space, and we can try to find a certain weight such that we consider vertical up here, and such that the vertical up, the proper transform of y inside this vertical up is the proper transform of x inside this vertical up is actually isomorphic to y. And to achieve this, what we want to do is actually we consider the valuation induced by the exceptional divisor on OX. And on the other hand, we also have a valuation so let me call this W. Let me call this S. So maybe this is again a quotient. Okay, so we also have a valuation called VW on OW. So we might hope that the valuation restrict to X equal to the valuation given by the exceptional divisor. So if this condition is satisfied, then it seems that we win. But here the one thing I need to explain is that what we mean by the restriction of the valuation, and also how do we compare this kind of restriction of valuation with the given valuation. Okay, so this is kind of the first step. So if we are successful in this first step, then we see that the given wettable the given divisorial contraction can be realized as a wettable in a very high dimensional space. And the next step is we can try to reduce the dimension. So at the beginning, the dimension n here could be very large, but then by some further technique and some further computation, then we can try to reduce the dimension n into something less or equal than 6. And then so this is step 1, and then step 2 we hope that n less or equal than 6, mainly by classification of three-dimensional terminal singularities. Okay, so we're expecting that the first part here is a very general technique that could work in arbitrary dimension, but in order to make it really useful and really to make it explicit, then we really need a classification of three-dimensional singularities. And this kind of classification, of course, is not exist in high-dimensional situations. Okay, so let's say. So what I want to do here is that we would like to introduce a notion we call it pre-valuation. So pre-valuation is so the original valuation is you can consider as a function from the ring to the positive integer to the non-negative integers, and satisfying the properties like this v of x1, x2 equal to vx1 plus vx. Also, we have the property that valuation of x1 plus x2 greater or equal to minimum of vx1 vx2. So this is and usual valuation also has another property that the value equal infinity if only if the x equal to 0. But now we want to consider the pre-valuation is given that this kind of condition. So we impose a weaker condition that Vx1, x2 greater or equal than Vx1 plus Vx2. And also we need this condition. So, and the reason we need this kind of pre-evaluation is that this kind of pre-evaluations behave. So suppose that it behave better when we take the restriction. So suppose this behave better under restriction. So for example, if we have a surjective morphism from R to X. Yes. Okay, and so then we can, and then given surjective morphism of rings, and also given a V to be a pre-evaluation on R, then we can define the restriction of V to S to be the sup of V Y such that y equal to X for any X in S. Okay, so we can define the restriction of pre-valuation by considering the sup of all valuations in the pre-image. And actually the reason we define it this way is kind of is associated to the consideration that given the pre-valuations, we can associate a filtration. And conversely, given the filtration, we can associate a pre-valuation. And moreover, what we can check is that this kind of association is so given two pre-valuation V1, V2 are two pre-valuations, and let me call this map to be phi, and the phi is injected. So phi V1 equal to phi V2 given only V1 equal V2. Okay, so in other words to say is that we can check whether two pre-valuations are equal or not by checking whether the induced filtrations are equal or not. So this sort of meet our purpose to compare the valuations of given by the exceptional divisor and also the valuation given by the weight. And actually we need to consider the restriction of the valuations, restriction of valuation to X, and but restriction of valuation is not necessarily a valuation, but restriction of pre-valuation is still a pre-valuation. So it's easy to check the restriction of pre-valuation is a pre-valuation. Okay, so this is how we check whether the whether the divisorial contraction is realized by wettable or not. We can try to construct the suitable embedding, and then we can try to find the suitable weight, and we try to compare their filtrations. And once their filtrations are the same, then we know the wettable give rise to our given divisorial contractions. Okay, so let me try to work out a little bit more about how we really so let me write down the theorem that, so suppose that R is a Noetherian integral domain. I forgot to mention that we also work on field of algebraical field of characteristics zero. Or maybe for simplicity, you can just or maybe just over C for simplicity. Okay, and so suppose there are two filtrations. Suppose we have two filtrations. There are two filtrations. A and R are satisfying say I greater or equal than Ri for I, and A1 equal to R1. And also suppose we know that the associated graded ring n minus 1 is a finitely generated R over A1 algebra. Then the filtration can be approximated by finitely many step of tilting. Okay, so here we introduce the notion of called tilting, and tilting is a kind of some notion in order to approximate the filtrations, and or in other words, to approximate the valuations. So okay, so our goal is actually try to, so just considering that B associated to B is given by our exception divisor, the actual valuation, and R is given by weight usually to X. So what we want to do is we might start with some testing. We start with some embedding when we start with some testing weight, and compare this weight with the actual valuation given by the exception divisor. Then we can just compare the filtrations, and so we sort of want to approximate the target filtration by our given by changing the embedding and changing the weight. So tilting is a method to change the embedding and to change the weight. So let me introduce the notion of tilting. Okay, so okay. So now given a pre-valuation, which is a function from the ring to positive to non-negative integers, then we consider the ring with one variable Rx, and then I want to consider the pre-valuation like this. So given a fx, the cosine is written like this, then we define it to be the minimum of V, C, I, and wait, I'm sorry. So I defined it to be the minimum of V, C now with VC1 plus A, all the way to V, Vn plus N times A, the minimum of this number. Okay, and suppose I have a suggestion map sending X to S, which is an element here. So one can see that if the A is chosen to be greater than the if A is chosen to be less or equal than the valuation of S, then the V sharp restrict to R is the same as V. But if somehow we choose the A to be greater than Vs, then the V sharp restrict to R is different from V. It's actually greater or equal than V. Okay. Okay, so this is what we mean by tilting R. So what the idea behind this is that if we somehow see something not matching, then what we try to do is that we introduce a new variable and then we change the weight a little bit. So in geometrical terms, it just says that we introduce a new variable and then consider the new embedding into the high dimensional space. So by this kind of technique, then what we can do is we can so what we can actually work is our algorithm is like this. So now we start with a threefold inside a four-dimensional space. So let me call it W naught, and then I have a curve in here, and this is an image of the excitation divisor. So that S1 to Sk to be a set of generators of the ideal. Okay, so now we start by considering R to be O W and introduce variable y1 to yk and then we introduce Vyi to be the valuation of Si bar if Si bar is non-zero, or we make it 1 if Si bar equal to 0. Okay, so by doing this, we associate a filtration, and one can verify that this filtration is bounded above by the B, which is associated by the exceptional divisor. And also we have the property that R1 equal to B1. Okay, and together with the property that the ring, the algebra, let's consider this algebra OY minus M plus YE, okay, is a finitely generated OX algebra. Okay, so this property can be seen by some standard technique of using vanishing theorem. And so by this finite generation property, and also by this kind of bounded property of these two filtrations, then we can see that after finitely many steps of tilting, we can approximate the target B by finitely many tilting of A. So this is the idea for proving that we can realize a wettable we can realize a divisorial contraction by certain wettable ups. And so by this kind of technique, then we see that Y to X can be realized as a certain affine space in certain wettable up over certain affine wetted space. Affine space. Okay. But next step, I would like to mention that we can actually make the dimension smaller as we like. So this mainly consists of computation of wettable ups. Okay, so now in this kind of embedding, all we can see is that X is defined by something like this. So X is the original equation may be given by F is XY 4-dimensional equation, and then we might introduce some new variable Y1, Y2, etc. That's a new variables. And probably a little bit more. So we might need more variable if we okay, so these variables are coming from the generators of the ideal in the, and this are coming from the approximation. Okay, so then what we did is that so we try to compute what happened to this wettable up, and since we know that three-dimensional terminal singularities that are always isolated singularities. So if we compute the Witten blow-up, then quite likely we get something non-isolated, especially if if this element S1 to Sk, if these elements are say of degree contains no linear terms, then it's quite easy to see that the power transform of the Witten blow-up has non-isolated singularities. So by using isolated singularities, we will see that S1 to Sk most one of and most one of it is nonlinear. When I say nonlinear means that the function here contain I say Si is linear if the function here contains some certain linear terms. So this computation shows that most of the function S1 to Sk they actually contain certain linear terms. So by changing the coordinates, we can actually assume that the curve in W is a locally complete intersection. In fact, it's a planar curve. Okay. So if we start with four-dimensional embedding, then actually we just need three generators. And if we start with a five-dimensional embedding, then we need at most four generators. So by this kind of computation, then we reduce the W A4, then K is 3. Okay, so by this kind of computation, then we reduce the dimension quite substantially. And the remaining task is try to find the number of steps that we need for the approximations. And this kind of step then relies on the case by case classification of the terminal singularities. Okay, so it's going to be quite a hard work, and that's why we're still working on this in progress, not complete the classification yet. But instead of giving you more proofs, maybe let me show you some examples that what we can see out of this kind of program. So let me show you some examples. Okay. So the first kind of example I would like to show you is maybe consider the easier case. So suppose that x is given by xy plus g u inside four-dimensional affine space, and suppose that the ideal C is given by y du, then we consider the weight to be 0 and 1 1. Okay, and where m is the multiplicity of G at the origin, then so in this example, then we consider this kind of Witten blow-up, then we'll see that y has a cyclic quotient singularity of type of index m. So it's a typical quotient singularity of this type. Okay, and actually a little bit more about the geometry is, so the exceptional, the preimage over, so this is curve C, the preimage over the origin is going to be have several components, and so let me call it gamma 1 over to gamma P, and the central point here is a single point, and the number of components here is actually given by the factorization of the G. So suppose that the Gm factorized like this, J. Okay, so suppose that Gm factorized into T components, then the preimage of the origin consists of T curves, and this each component pattern through the unique singularities, unique quotient singularities, and also if mj equal to or equal than 2, then suppose that m1 equal to or equal than 2, then there's another constant singularities here. So each example, then we can have a very explicit description like this. Maybe I can give you some more examples. It will be more complicated examples like this. So suppose that x is given by xy, again a type g d to the r u inside this four-dimensional space. So similarly, that n to be the multiplicity of g at the origin. Okay, and then what we, and in this case, we will require that we need another extra condition that a should be relative prime to n times r. Okay, so under this condition, then we see that if zr divide g, then there is this I'm sorry, I should say so again we have gamma 1 to gamma p. We might have t components, and t component again depending on the factorization of
What is
g
C
here.
here? Excuse me,
What is
Jungkai.
c?
Yes.
C, let's see, what's c? There is no c.
It's the bracket, the opening bracket, I think.
Yes, so there's
And the same two lines below.
This threefold singularity, and you need curve which is what you going to blow up.
I'm going to blow up the. I'm going to take the multiple of this four-dimensional affine space.
Yes.
So
Yeah, but
okay, yeah, I'm sorry. So I should tell you the weight. Yeah, so the weight is 0m11 again.
I see. This is just coordinate.
Yes,
line.
yes. So this is a weight assigned to each coordinate, and then we see that the upstate there's a single point of index m times r 0 a n minus a minus a. So So upstate is a singularity of a very high index, and this is the origin here. And also the number of components depends on the factorization of G here. And in some cases, they might have some extra. If ZR divides G, then there is another quotient singularity of CA over R. And if ZR does not divide G, then no other non-constant singularities. Okay, so there are another example like this, and there are actually a couple more examples. So currently we have about 20 something examples already, and we expect that this kind of complete this. So we are still working on checking all the calculations and checking whether the this is complete or not. So we're still working on this. And yeah, so we hope that by this kind of classification, then we have a better understanding of the threefold geometry, and also some part of the technique might be helpful to study the high-dimensional geometry as well. So I think my time is up. I stop here. Yeah, thank you very much.
Thank you. Any questions?
I have maybe a couple of questions. Your curve, do you assume that it is somehow smooth or not?
No, it's not necessarily smooth.
It can, basically, I think that it can be can have arbitrary singularity, right?
Yes, but we can show that it's actually at what's locally complete intersection singularities. And the reason is that if the singularity is too wild, then the weighted blower will produce non-isolated singularities over the origin.
When you say locally complete intersection singularity, means that as an abstract curve, right? Not inside.
Right.
I see. And another question: in some cases, there is there are examples and descriptions. These divisorial contractions by Mori, for example, for semi-stable case. Can you compare it this one?
You mean can we reproduce those examples?
Yes.
Yes. So I think we check those examples by Mori, and also we check those examples by Ziodas. And yeah, I think our method cover those examples.
I see. Because, for example, in Mori papers, there is some algorithm for semi-stable contractions, which is quite complicated.
Yes. And yeah. So the algorithm is yeah. I think our algorithm is kind of little bit different approach, and also different from Nicholas' approach, because we sort of guided by valuations.
I just want to say that it's not the answer is not so simple, not just to in his case just to describe this neighborhood of the upstairs variety. He's use quite complicated technique. I mean that.
You mean the extreme neighborhood?
Yes,
The
yes.
classification. Right. So yeah. So the classification of extreme neighborhood is it's quite dedicated and also not very simple.
Yes,
And
I see.
yeah.
Okay, thanks.
So more questions? If no, thank you, Jungkai, once again. Thank you.
Okay. Yeah. Thank you very much.